In this video tutorial, we're going to show the process of designing a two-way post-tension slab in AdaptBuilder 2019. We're going to go through the process of applying a few gravity loads and also defining our support lines in order to generate design strips, modeling the post-tensioning, and then running through the analysis and design of the strips for the slab. We're going to be working with a fairly simple slab here. It has a few interesting things about it, particularly the column layout. So we need to define, essentially before we start defining the strips, we need to determine how the tendons are going to be laid out schematically for this type of a slab. We're going to start by selecting the slab. We'll go up here to loading. We have under load cases just two reserve load cases, dead load, this would be superimposed dead load, and also live load. This is unreduced live load, so we're going to go ahead and add some loads here. I'll select the slab region. I'll use the general patch load wizard, and for the dead load we're going to say that the dead load is 20 psf, 0.02 ksf, and then I'll go back to that same tool and I'll assign the unreduced live load here as 50 psf, 0.05 ksf. And we can see it's hard to see the loads in this view. If I go to a 3D view, this is the top front right perspective view, we can see those loads. If you double click on the load, you can modify or edit the load. You can also, under loading, use the option here for show all loads or view load settings to obtain more graphical information about the load that has been applied. So here we could select dimension, and this would show the magnitudes for those two loads that have been created. I'll go ahead and turn the loads off. I'm also going to add a line load. So to add a line load, I can use the line load wizard or just add loads using these general options, point, line, or patch. I'll use the wizard again, which maps the load to the perimeter of the slab, and we'll say that this load is going to be 0.35 kips per foot. Okay, and my line loads are then shown. Again, I'll turn the loads off. For the material assignment for this particular slab, if we double click to open the properties, we can see it's set to concrete 1. I'll go up here to criteria, concrete. I'm going to change that to 5,000 psi concrete with adjustments to the modulus and the other adjustments as needed for this particular design. We can also define our reinforcing material, pre-stressing material. We'll leave those put as they are now. We will also go over here to allowable stresses, make sure we have the proper allowables set up for the slab. We have sustained and total allowables shown for compression and tension stress, as well as the initial condition. These are pulled from the code that has been defined here under design code, which is ACI 2014. There are additional options shown in this criteria menu that the user can fill out. We're going to leave these set to the defaults for now and continue on. So the next step is going to be to set up the design strips. We'll go ahead and under floor design, we can either use the options to manually create support lines. So if I, for example, wanted to select create X, I know that I'm going to have support lines in the X and the Y directions. Now let me back out of this just. So we know in this particular example, we're going to align the banded tendons in this direction. We'll just assume this end here is the dead end. We have live end. The spans are short enough to where we can stress from one end, and we'll do the same here. We have a banded tendon here. This area gets a little bit interesting in terms of the post-tensioning, but we're going to make a decision where we can stress in the openings. So maybe we have another banded tendon here that's stressed. Over on this side, we're going to do something like this where we stress out around that column. We might group that there, and then on this end I'll dead end a tendon here and do something similar on this side. So this could be done multiple ways. These are fairly long spans where we may not want to bring a tendon all the way through here with like a low point in this long span because we have some columns there that are affecting the behavior, the deformations of the slab in that region. So we'll leave it as shown without this tendon passing through continuously. In the other direction, we're going to use our uniform cables, and we'll just space those at some set distance. and we'll put the uniform cables in that direction. So we want to lay out our strips, especially in the banded direction, kind of according to the flow of the tendons in that direction. And we're going to start by showing the manual input of a support line. So I can use create X or Y. I'll just go ahead and snap on the end point of the wall, on the opposite end point, this column support, another column support here, and then I'll end at the slab edge, and I'll just press enter to close that. And I could continue going through that process. Now another option would be to use a dynamic editor. And here I can select Wizard X direction, and then I can just pass a construction line. This red line is our construction line. If I want to snap at the ends of, or have the program auto snap at the ends of this wall, then I just need to pass through this column to pick that up as a support, click near the end of the wall, and pass through that column and press enter, and that will automatically create a support line. The same thing here. I'm passing through all three columns. The program will add vertex or nodes rather to the support line at those column locations, and we can just continue on down the road here, adding these. Now, I do want to capture the effect, especially the negative bending effect near these columns. We know we're going to have tendons passing through here, so I could do something like this. Just add another support line in here and make sure they're aligned with these columns. And I'll do the same thing right there. I also want to do this at this wall. This is clearly a support for the slab, so I'll just click out here. Go ahead and say no to that. Let me try that again. Let me reopen that. So coming back to this, I'll select the option to where I click near the endpoints of the wall and then enter to close. So those are the strips for the X direction. I'm now going to switch this to the Y direction, and we'll do this direction. I'll pass through these first two columns. I'll swerve over to hit that column, up to hit this column, and then I want to click at the endpoint of that wall and then vertically, and that picks all those points as support points for that support line. I'm going to flip over to this other side here on the right edge. Okay, and that's the support line there. Here we have a few interesting characteristics about the support lines. Again, I want to follow the layout of the banded tendon. So I'm just going to select a point somewhere behind this column. That's where the dead anchor will be for the tendon. And I'll just snap like so down to this column, and then let's say perpendicular to the slab edge. On this side I'll do the same thing, but here I'm just going to snap near that center point of column. Okay, so these two tendon lines are going to swerve into that one support, and then I'm going to go ahead and close this. I'm going to do the other ones manually. So when I create these manually, I can select snap to nearest. I can snap on that opening face. I'll turn that snap to nearest off so that I can easily snap on the columns, and then I'll snap here to the center, or the perpendicular to the edge of the opening. Press enter to close. I'll go back, snap to nearest, and then we can align this column here. I'll turn off snap to nearest, and I'm actually going to take that and pull that back using snap to intersection. And that's the Y direction support lines. Now, one other thing that we could do is I could add support lines along this wall and this wall. We're not going to. I want to show you another feature within the program that we can use to deal with these two walls. Okay, we have not put in any splitters, and if you're familiar with the older versions, splitters could be a very intense part of trying to get the proper design strips. We're going to pay particular attention to the openings and what happens with the design strips near these openings without any splitters. And I'll first, from the floor design, I'm just going to generate my design cuts. And I'll come over here to strip results, visibility. I'll turn off both directions and then just toggle to the X or the Y. We'll look at the X first. And we can see the program generates these strips. These are just tributaries. If I turn on the tributary region, you can see they're colored. But let's go back, and we can see, for example, here, these strips cut into the opening. By and of itself, that is not a problem analytically. The program is only going to generate the design actions as a function of the nodal integration over the portion that's actually within the slab, not into the opening. If the user wishes to cut out the opening from the generation of these sections, then what we can do is the following. I'm going to go ahead and turn off the section cuts, and I'm just going to add a splitter. I want the program to terminate this cut at that line and at that line. The splitter is just a boundary that allows you to dictate how wide the tributary is perpendicular to the boundary. So I'll use an X splitter. I'm just going to add this along this opening edge and along this opening edge, and that's our boundary in essence. I can do the same thing, for example, down here. I want to add a boundary there and there so that the slab sections don't cut into the opening, and I'll do the same thing here. Okay, so there's six splitters. We're going to regenerate the cuts, and now we have these openings bound out from those design strips. So that's the completion of this actual portion of the slab. We'll switch over now to the Y direction, and we see we have kind of the same thing going on. This extends through the opening. The same thing here. This actually extends into the opening and out of the opening, which we definitely want to avoid. And here you can see there's a little bit of overlap right there with these sections, and also over here. So I can use splitters to handle all of these things. I'll go back, turn off my section cuts. I'm going to turn off my splitters in the X, and we'll go to use the splitters now in the Y. And first thing I'll do is just add a splitter on each side so we don't extend into that zone. Same thing here. I'll add the splitter on these sides of the opening. And where we had that overlap, I'm just going to go and add a point from there, and I'll snap this to the mid distance of this opening face. Could also add something like this and something like that. And what that will do is that will eliminate the overlap from this design section and this design section in terms of the cut lines. So we'll go back and regenerate again. I'll turn on the sections, and this is now what we end up with. You can see that line delineates this section cut from this one. This line does the same there, and then this splitter, rather, not line, but that does the same thing there. And then here we have the sections coming over and hitting that splitter. They don't extend into the opening. Now, one thing we do want to avoid is having a design cut extend over a wall, like here and here. When that happens, you can see that the support line is actually over here on this column line. These reach all the way over and extend over the wall. If a design cut extends over a wall, we don't design the cut for ultimate level demand, meaning for strength combinations we don't produce any reinforcement. We only reinforce these cuts for minimum reinforcement. And also we wouldn't show the stress for the flexural stresses, compression or tension for the cuts that extend over a wall. So one nice thing with this version of the program is we can tell the program ignore or apply the boundary condition for these walls relative to the Y or the X direction. And I'll go back to Dynamic Editor under Walls, and I'm going to say User Defined. I want this to be a Y boundary only, and I'll select that wall and that wall. I'll close that. If I regenerate the strips now, you can see that these cuts extend just off the face of the wall. And that's one way to use those boundary conditions set in that dialog under Dynamic Editor for strip modeling. Okay, the next thing that we're going to work on is modeling of the tendons. So before we actually analyze the slab, number one for punching shear, and then we're going to look at flexural design steps, we would need to model post-tensioning. That could either be done manually with replication, or we can use some of the mapping functions in the software, and we're going to show you both here in this video. So the first thing we're going to do is actually turn off the strips using the visibility options. I'll turn off the splitters, and we're going to just isolate and look at the Y direction strips first. And I'm going to go ahead and use the option under tendon. We're going to map the banded tendons. And before we start mapping, we want to define our tendon heights. So for this slab, under the tendon height defaults, we're going to have 1 inch. If I draw a slab here, maybe this is a support, and we have a tendon that drapes low and then high over the support. This distance, tendon from top fiber, is the distance here to center of gravity of that steel. And then here we have this distance, which is CGS of tendon from bottom fiber. If the program ends up pushing the tendon vertically or bringing this down, let's say in terms of balance loading, the program will use increments of 0.25 inches. Okay, so we'll leave this set to 1 inch. We just want to make sure that the user is aware of that definition. Otherwise, if you wanted to use something different and it was using the default, then you would have to go back and modify the CGs of the cables, which can be done rapidly through our tendon editor, but it's always good to specify the requirements first. So let's go ahead and use the mapping function here. We're going to map banded tendons. We're going to use the design strip width to generate the post-tensioning force necessary to meet a couple of optimization parameters. That is precompression and percent of self-weight to balance. And here we would set our preferences. We're going to balance 125, let's say, to 300 psi for precompression. And we want to try and balance the self-weight maybe 50 to 100% of the self-weight to balance. The program is going to target those two options and those two sets of criteria in order to determine a force and the initial profile of the tendons passing through this strip. The tendons can be placed either by a group of 2 with offsets. So we could, let's say we need a total of 10 tendons for this strip. The program would offset this by 2 feet or whatever the user inputs here to one side and 5 on the other side. So we'd have 5 and 5. And this historically has been the way that the balanced or the banding has been done for mapping banded tendons. The user could also use one group. So maybe instead of having 2 times 5, we have 1 times 10 with an offset. Or we could also just have 10 individual tendons spaced at some distance between the tendons with, in this case, we would have 5 on one side, 5 on the other side. This is more detailed of an approach. You probably don't need to go that route unless you have very, very sensitive deflections and you wanted to replicate how the tendons would truly be laid out in the field. So we're going to just use the default 2 groups, and I'll set this actually to 1 foot. The program will replicate this exact support line. So one of the tendons potentially could actually fall outside of the slab. That's the first thing. And also the tendons will replicate the spans. So there's going to be 1, I'll mark these. There will be a cantilever span, I'll call it cantilever top. And then there's going to be span 1, 2, 3, 4. And then this tiny little span here will be actually cantilever bottom. So because I input the points like that, or the generation using the wizard input those as such, we have to deal with the fact that there's going to be a tendon span at those locations. But that's easy to deal with. We'll show how you can modify that fairly rapidly. So for each tendon that's placed, we have to specify some initial estimate of the effective force per strand. So this number here, 26.7, would represent the effective stress in US units. That's 175 KSI times the area of a strand, half-inch diameter strand, which is 0.153. That equates to 26.7 kips per strand. And the program again will tell us how many strands are needed to meet this criteria here. We can also define the shape of the spans. So in this case, the first span might be this span here. All of the mid spans, or the spans I'm just putting an X through, the last span is this span here. Now I'm not going to actually change these to cantilever down or cantilever up. we're going to just rapidly go through and modify all of those using the tendon editor shown here. So I'll just leave this as is, say OK, and we can see the tendon maps to that support line. This is actually inside of the slab, so we don't have to modify that. But if I look and double click on one of these tendons, we can see there are 7 strands times 2, so there's actually a total of 14. Under stressing, the effective force is 26.7 kips. We can now switch this over to calculated force if we wanted the program to calculate the force and the losses for us. That's an option. We can do this either individually through this interface, or I could select multiple tendons at the same time. Maybe I want to turn all of them to calculated force once I'm done mapping. Then I could go to modify the selection. Under tendons, we could go now and change this to calculated force and define the properties for all of the selected tendons. We're going to leave this to effective force. Okay, the shape of the tenon looks like this. Now this is where we get those 2 spans on the ends that are, these are cantilevers, especially this one. This is a true cantilever. This one over here is a cantilever only by modeling only. So in reality, we're going to drop this cable down to CG and then just run it straight out. This is a 1 foot plus span, so we don't need this reverse parabolic shape in this case. So I'm actually going to go to this span. I'll go to the left or the right side of this cantilever. I'll change that to 6. Remember, this is top down. And I'm going to change that to a straight, or let's say a cantilever down shape, like so. Okay, that's one way to modify that tendon. Another way to modify the tendon would be to go to Tendon Editor. You can see the program marks the spans in this yellow square. That means those are editable. And if I go over here to Shape, Cantilever Down, notice that right now one is cantilever down. That's the one I changed. The other one's reverse. I'm just going to select those and it changes those spans. I'll pause this, and if I double click on this one, you can see that that still has that sharp kink in it. I didn't push that down to 6 like I did the other. So I'll come back into the editor. If I now turn on CGS, you can see that this CGS here, both CGSs are 1, so this one actually didn't take. Let me pause that again. I did not click the green checkbox to accept that change. I'll do that now. I'll select that. Now if I come back and resume, this is 6 and 6 and 1 and 6. So I could just change these again rapidly by just selecting that. And again, we could have multiple bands that we want to change at once and select everything at once. So we're going to go through over on this side. I can tell that this is actually a reverse parabolic shape just because you can see these blue points. Those are low points, which would not be there if this was only a 2-point defined shape, which is like a cantilever down shape. So if I come back into the tendon editor, I should not have closed that. I can go back to shape. We're going to change this to cantilever down. If I go back to CGS, 1, remember at the high point, this is our control point. You can tell it's a control point by that little square, that handle. I can actually select and move that. So this is 1 inch from the top. Okay, so this is 1 inch from the top of the slab. This is 6 inches from the top. So if this is a 12-inch slab, you have 11 inches from the bottom here and 6 inches from the bottom here. If you look at an interior span, this blue point is the low point, so that's from the bottom up. Remember, if this again is a 12-inch slab, this is 1 inch off the bottom of that 12-inch slab. And this is how we would define our cables in that case. Go ahead and close that. I'm just going to go ahead and select all of my strips. We're going to map everything at once and then go back and clean them up. So I'll go back to Map Bandit. I'm going to use the same input parameters. I'll just say map that. And there's a few issues here. We can see that the pink indicates that the tendon is actually crossing into an opening or outside of the slab somehow. Here, this is slightly out of the opening. So before I do anything, if I wanted to trim and extend the ends of tendons to the slab edge, I can just select everything, go to trim and extend the tendon, and that fixes some of these. We still have an issue with these passing through the opening, so I can go and just move this, for example, away from that opening. There's my opening edge here, and I've moved it outside of the opening. I'll do the same thing for these cables here. Okay, and this is just a function of the mapping. Remember that we're mapping 1 foot, and it's a pure 1 foot offset from the actual support line. So we may have to make a few adjustments like this. This one, which is right on the edge of the slab, I'm actually just going to delete this tendon, and I'll have one tendon represent this last strip. If I double click on this tendon, it's 6, so we know that there was another tendon of 6. We'll make that 12 and be done with that. And the next thing we're going to do is come back and adjust the cantilevers again like we did for the tendon on the left. So I'll turn off my strips. I'll go over here to Tendon Editor. The first thing I'm going to do is modify the shapes. So this is reverse parabolic. I'll modify that shape. This is already this is a cantilever down shape. We're actually going to want to change that. We don't have a reverse option here, so we'll come back and manually change that. Here we have a reverse parabola for these two tendons. Same thing here in this span, and this span, so that's fine. Over on these tails, we're going to use cantilever down. Those are going to anchor down to the CG of the slab. And then you can see these are all reverse parabolas here. We're going to change this one to cantilever down. There's a high point there, and there's also a high point here. I'll change that one to cantilever down. And then if I go over here to CGS, we're going to drop the CG to 6 on those. So that will become 6 there and there. And then this one, we're going to drag these out to the edge of slab, something like that. We can just straighten these out. Okay, so all of these tendons are just kind of ending at this support here. We're going to have fairly high precompression there because of that, and then they split to go to either side of this opening. If I come back into the tendon editor, I may need to make changes to the CGs elsewhere. So we can see this is a reverse parabola. There's a wall there, and we don't really need drape in that span, so I'm going to change that to 6. That will run straight down to the CG from a high point here at this first column. This low point is 3.25. The program had lifted that up to maintain the balancing. And then again, we have a situation here where we want to cantilever down because of that short span, and I'll change the CG to 6 again. Everything else looks fine, except this span needs to be a reverse parabola. So we can do that by double clicking. You can see that needs to be a RP. We'll change that there. And then we'll do the same thing for this one. Now let's go ahead and save the model. I'll go over here to visibility and to render model. We want to look at these tendons to kind of get a sense of how they're shaped and profiled throughout the slab. I'll turn off my columns and walls, go to a wireframe view, and then I'm going to zoom this in the Z direction. So let's do by a factor of 3. And now we can see the tendon shapes. Okay, so this shape over here, we had changed that to 6 and 6. That we need to check that out. This one right here needs to be dropped down, and then these two, we probably have too much drape on those. We could fix that. Let's go ahead and take a look at that. Okay, let's go back and reapply that. So that changed that CG, and then over here We're going to go to shape, make sure that those are cantilever down, which they are, and again the CG here will be 6 and 6. We'll close that. You can see right here, this, we may want to change that shape to a straight shape. We have 3 points defining the profile. We're going to just have 1 and bring that straight down. We could drop that CG down also if that's raised too high. And then here we're going to just modify the CG. These are maxed out in terms of drape. This is a short span. It's a 12-inch slab, so I'm going to modify the CG there to 6. And if we double click on one of those, we can see we're just lifting that up to reduce the balance loading in that span. And finally, we may want to straighten these 2 tendons out here. So we'll just straighten those out. This one we could just align and use perpendicular snap to align that. So there's a few little cleanup things like that that we can do. Now that we have the banded tendons, we're going to model the uniform. The uniform here, we're going to break this up into really a few zones. We're going to have zone 1, zone 2 here, zone 3. This will be zone 4. And then here we'll have zone 5, let's say 6, zone 7, and then maybe 8, 9, and 10. So this, where you have all of these unique regions where we would have different spans relative to the other region, we have to break that up into how we map that. But the first thing we want to do is just determine a spacing of the tendons and then how much force is needed to meet pre-compression for that spacing. So we're going to say, in this case, we're going to space the tendons every 4 feet. And if we look at the slab thickness, again, the slab is 12 inches thick. So for the 12-inch slab, the area of a 4-foot wide strip is 576 square inches. If we multiply that by the target pre-compression or minimum pre-compression of 125, we need 72 kips per 4 feet. And 72 over 26.7, we need basically 3 tendons every 4 feet to get enough pre-compression in the slab. So we're going to start by just modeling. We're going to add a tendon manually, and we're going to model this tendon. I'll start at the left, work to the right, and I'm going to turn on this option for perpendicular mode. And we know we have a cantilever on the first, let's say, first span. This is a cantilever, so I'll click a point. This is defining a control point, a high point at the banded tendon line, another high point, and then we're going to just terminate this over on the I'll turn off snap orthogonal. We're going to terminate this on the right hand side. So this is our master tendon, and we can go ahead and define this. So this is going to be 3 strands, and then we're going to copy this down. So 3 strands, and we're going to say, okay, this tendon, the effective force is 26.7. That was our assumption for force. And under the shape, we're going to have a cantilever on the left side, cantilever down, a reverse parabola, and a reverse parabola for the 25-foot span and the 34-foot span. And then we're going to copy that down every 4 feet. So I'll go to modify. I'm going to copy that by coordinates, and this will be in the negative y direction, negative 4 feet, and I'm just going to copy this 15 times. Okay, and we can see the layout of that set of cables. Now these points right here, those are static. Those don't move because we copied them from this master tendon. Once I get below this point, then we'll have to adjust that. So let's go ahead and take this now. I'll just use the same command to copy negative 4 feet, and I'll copy that over, let's say 10 times. We're going to have to do some adjusting here. So now I'll take these tendons here, and I'm going to turn on snap to nearest, and I'll just start to slide these points over so that I adjust the cantilever, and this is ultimately adjusting the low point in this next span. So that's the first thing we'll do. We'll just leave that one as is. We're going to have to make some modifications elsewhere. We could also adjust these in here, we'll just drag those over slightly. Delete that one. And now this tendon here, I'm going to actually just take this tendon and say, okay, here we have a wall, so I'm going to adjust that actual tendon. Let me save this, and we're going to say for that tendon I'm going to move this point over. But I also want to right click and I'm going to insert another point. So this inserts another high point, and that other high point is there. So I'll just move this tendon here along this wall. And if I double click on that span along the wall, which is span 3, I don't need any drape there. There's a wall there, so I'll just make that straight and be done with it. Okay, the same thing here. I'm going to manipulate this. I'll go ahead and take this tendon, and by the way, this tendon, since this grows, this area right here, I'll just bump that, see that number of strands, maybe I'll bump that up to 4 versus 3. On this one, I'm going to right click and I'm going to delete point 1, or rather point 4, and then slide this over to the face of the opening. Make sure that's perpendicular. And now we have this. We have the cantilever and then one span to the opening face. I'll take this tendon now and I'll just copy that back up one time. So there's a copy of 4 one time, and then I'll delete out some points starting at the left side. So I'll delete point 1 and point 2. And now we have a single tendon on this side. Okay, and that cuts it out of the opening, and we have this one which is basically over the wall. We'll go down here now and make the same type of modification at this opening. So I'll right click, delete this point, extend that back over. Here I'll do the same. I'll right click, delete this point. I'll take this one and copy that one back up, and then I'll delete from the left. So we'll copy this up twice, 4 feet. Make sure you select the right tendon. Here, the first tendon I selected was actually the one I just modified, so I want to make sure I have this one selected. Right click, delete points 1, 2, and then we're going to just slide this one over there. Now I could just say, well, just copy that one back down that I just modified, so that's easy enough. We'll take that at -4, copy that down one time. Okay, we're now going to take this tendon, and I'll go ahead and copy that down, use my replicate again. We'll do this -4, just one copy, and again we'll use the delete option to manipulate this. And I'll take this one down and copy. Now there's this, now we really don't have a cantilever that's stopped in this bottom span. It starts to grow as you move vertically. So I'm also going to just delete out this extra point. And now we just have a simple, really just a single span, but we need to make sure we have the right shape. This is a reverse parabola, and this distance should be 6. And now we can take that and copy that down a couple of times. Say this is -4, and we'll copy that. I forgot to add 2 there, so copy it one more time. And we can see this is actually below the opening, so we're going to now just stretch this one out. I'll stretch it all the way over to this side, but I only have 2 spans. I have actually 1 span from this point all the way over to here, so I really need 1, 2, 3 spans. I'll go ahead and right click, insert a point 1 and point 2, and then I can take those points and just move them where they're needed. Okay, and if we look at that shape now, we have this, but we need to adjust these 2 points back to 1 and 1. So it's always a good idea to go back. If you copy a tendon like that and add new points, just go back into this dialog, make the necessary modifications, and then it's much easier to control what you're copying and replicating. So we're just going to now copy this down several times. I'm using that 4-foot spacing, remember. We'll do 8 copies. There's a few too many. I'll delete out the ones I don't need. And now we have these, again, we have these short spans that are converging as we move down the page. So I'll just move these over just to align those with the bands. We don't really need much drape between these two bands, so I'm going to take this tendon and say for that middle span, I'm just going to run that straight over the two bands. The same thing here. And finally, for this one, these two bands converge, so really we have a two-span condition now. And I'll just right-click and I'll delete out one of the spans. So I'll slide this control point over. Now we have span 1 and span 2, and if I double-click on that tendon, we should see that like so. Okay, now the last portion is this portion over here on the right. I'll copy this tendon down. I'll copy that twice. And then I'll delete out the points that are unnecessary. And we'll just move those back into that position. And turn off snap to nearest. Okay, and this finishes out the tendon modeling. Now, in terms of CG, there's a couple of things here to note. Whenever we're editing a tendon, either through the individual tendon property box, remember that the CGs at the top are top down, if the anchor is top down, bottom is bottom up in terms of their reference control point. If we go to tendon editor, that's defaulted to in terms of the same reference. So if I go to CGS, again, all of the bottom CG marks, these blue points are bottom up, the top points are top down, the control points. The anchor points are top down. If I flip this and I actually want to go and just, let's say I'm managing the data in order to export it out as a DWG file, and I finalize my design. If I use the display manager, not the editor, but the display manager, and I turn on the control points, now all of the CGs are always bottom up. That's the reference, the soffit of the slab. So you can see rather than having these at 1 in editing mode, these all become 11 because we're going from bottom up everywhere. So that's one thing to note. You may see that. If I want to control the text, this text is a little small, we can always go to visibility, view settings, control really graphically anything in the model, and under loads I can go ahead and, under components, finite element, tendons, I'm just going to increase and double that font height. And now we have this in terms of the view that we're seeing from the actual display manager. I'll turn that off. I'll come back over here to visibility, render model, just to have a final check of my tendons. I'll turn off my columns and walls, and this now becomes the layout for my PT in this model. This is really just our starting point. We're now going to process the analysis and the design of the sections, and we're going to look at a few ways to review results in the model. Okay, so let's go ahead now to analysis. I'm going to mesh the slab. We're going to mesh this using simplified meshing. This is more appropriate for a single level slab design versus a multi-story lateral analysis where we might have openings and walls. We may need to switch over to advanced meshing in that type of an environment, but we'll just leave this set to the defaults. I'll save and mesh the slab. Once I've meshed it, I'm going to analyze it. Now the analysis options you see here that has a few load combinations. These are defaulted to based on the code that we have selected. Here we have ACI 318.14 selected. Under loading load combos, these are defined here. The user can add additional combos as needed. Those combos can then be used over and over and over again. We have a couple of videos in our YouTube channel that shows how to take how to take combinations from one model and maybe produce the same in a list for another model, either by use of the IMP format or through the Save as Template option, which is up here in the File menu. But I wanted to just point out that these are the combinations that we're going to be evaluating. We have a couple of service combinations, which we'll mainly use to check pre-compression, balance loading, and stresses, flexural stress. Strength combinations will be used to check what their punching shear design is for the two-way shear check, and also just longitudinal or flexural checks at ultimate level forces. So the initial check would be checked against the allowable stresses at initial condition or at transfer condition when we transfer the force to the slab, which has a different threshold value in terms of the allowable stress than regular service total or service sustained conditions. All right, so let's go ahead and close that. I'm now going to go to analysis, and we're going to execute the analysis. And it's important to note right now we're working in single level mode. So up here at the top, you can see we're working in single level mode as compared to multi-level mode, which would mean we might be globally analyzing a multi-story structure. This is really applicable only to single level, what we're looking at now. So that doesn't mean you can't switch to another level and work on that in single level mode, but when we're processing this type of a slab, make sure you're in single level analysis mode. And we'll go here to execute, and I'm going to run the analysis for this slab. So that's done. I'm now going to go back to divisibility. I'll go to my default display, which is set up under View Settings. We select our default options, Save as Default. And before I continue with the actual design of the design strips, I'm going to just check punching shear. This would be a good time to maybe check deflections based on just the linear elastic solution to make sure we're in the ballpark of proper deflections and within those limitations, and also to check punching. So I'll select under Floor Design, under Shear Design, make sure you've gone through and set up the proper checks for punching shear. I'll use a 3/4 inch diameter stud. I want to limit the rail spacing to 2 times the effective depth. I'll provide uniform spacing of studs, and I'll consider critical sections outside the shear reinforced zone. So we'll say OK. We do have a video that defines this in more detail. Again, on our YouTube channel, you can search punching shear, and you can get more information on these options here. Once you've set up your shear design options, we're going to execute the shear check. Under the result browser, which will open at the right hand side, under the loading tab, I'm going to select the envelope of strength. And under analysis, I can go to punching shear, and I can review the punching shear results. So you can see there's several columns here that have been checked for punching. There's a few here that actually say not applicable, and the reason for that may be that this slab needs to actually stretch out slightly in order to have those columns checked. So if I actually take this slab, I'm just going to move it out just a bit. That'll actually grow the area for the tendons on that side, but we'll ignore that for now. Okay, so let's go back, and because I moved the slab, I'm just going to remesh this and just update my analysis. You could go back and just check the punching there, but I'll execute again. We have a little more load on the perimeter based on that modification, so we can run through that again, and then I'll just go back to Floor Design, execute the shear check again. Okay, and if I select this, you can see those are now checked. So there's just some anomaly where that slab cuts through the column where we just move that out. Now the reason this is not being checked is it's touching this wall. So if you create a gap there, or if we were to select this column and disregard it for finite elements, we could get a check for that column. But right now that's not being checked because of its proximity to the wall. You can see the program tells us that there's several columns that need reinforcement. We can also check stress ratio. This is being checked separately about the R and the local R and S axes for the column. Condition, this just tells the user what condition is the column. By the way, you can see the colors are somewhat muted, and that's because the upper columns are actually not being checked. So if I take these columns, right click, hide the selection, it becomes easier to see those colorization of the columns and the different conditions. So these columns on the interior are blue. That means we're checking a four-sided critical section within the reinforced zone of the shear system, i.e. punching rails or shear rails. And then we also have columns that are orange. That means these are within proximity to this opening where we're actually considering those as end or edge conditions. It's somewhat conservative in this case. We have end edge for these three, end edge here. Here, that's basically a three-sided critical section within the shear reinforced zone. Beyond that, we check it as a kind of a half octagonal shape. Interiors outside the reinforced zone we would check as an octagonal shape, and then we have two corner columns here on the left and right side at the bottom face. So those are the different categorizations of the punching shear check. And ultimately, we could get reinforcement shown here. This just gives a kind of an abstract or a shorthand version of what the reinforcement is. This means that we need 8 rails total, 2 rails on each side. This just shows a line, a vector, the direction of the rail, and this is to scale the length of the actual rails. So we have 2 rails each side of this column, and we need 4 studs at 5 inches on center on each rail, and the total length is 20 inches for the rail. So that's how you can determine what the reinforcement is on the columns. Ultimately, we could go over here to reports and produce a punching shear reinforcement schedule for the columns. But what we're mainly looking at here is that we don't have any conditions where the stress check exceeds the code allowable, or the maximum allowable stress, for this case 8 square root F prime C, and I can determine that by just seeing what the stress check status is. Everything is reinforceable in this case. Okay, so that's a quick introduction to the punching shear check. Again, we have other videos related to that you can review on our YouTube channel for more information. The next step would be to go and design the section. So before we do that, we're just going to get a feel for what the deflection is. If we come back to loads in the result browser, I'll go to the total service condition. This again is a linear elastic solution. There's no long-term effects. There's no cracking in this case, but we're going to again just check ballpark type figures. So under analysis, slab deformation, we're going to look at the Z direction deformation, and we can see maximum deformation is 0.33 inches, and that's out here on this cantilever. Once I produce this contour result, I can go back to visibility under render model, and in this view we could, let me scale that back to 1. I'll just zoom in there. Okay, so if I use this kind of warps the slab. We get just a generalized relative shape of the deformation. This is Z direction. Maximum deflection is actually out here on this tip. So the user would then be able to determine, okay, under linear elastic conditions, if we apply just a multiplier maybe to predict long-term effects on top of that 0.33, does that satisfy the requirements and the limitations for deflection control in different regions of the slab? And there are ways to predict the long-term deflection and the cracking in the slab. Those are reviewed in another video. But the 0.33 is just an immediate deflection under service total load. So this is unfactored load for dead, self, and live load. You can also turn this to a deformed shape, which is just more realistic. We can adjust the scale of the deformation here. So this is kind of what the deformed state looks like for this particular slab with tendons in place. Okay, and we can see here we have about 0.2 of an inch of deflection. Again, max deflection is about 1/3 of an inch of deflection here on that cantilever. Now, as we adjust tendons in order to meet some of the requirements for the post-tensioning in the slab, that deflection would change. So once we get downstream into a design, the user would typically then check crack deflections and long-term deflections in the program. The final thing we're going to look at in this video are the design strips. So we'll go to floor design. I've generated the design cuts, and now I can toggle between X and Y. These are yet to be designed, but we'll go ahead now and design the design sections. So the program is processing the design of each of those sections for reinforcement, for stresses, pre-compression, and balance loading. Once that's done, we typically recommend to the user to just isolate one direction. So we'll isolate the X. We can select the load combination we're going to check results for. We'll say here again is service total. Under analysis, we'll go here to design sections and stresses, and we can then start reviewing results necessary to meet the design objectives for a PT slab. This is a PT monostrand unbonded system conforming to ACI, so we have to meet some minimum level of pre-compression. We're going to check the top and bottom extreme fiber stress for tension or compression. Balance loading, we may want to determine what the balance loading is for the slab. We can start with, for example, pre-compression. I'm going to use number of tendons. This just means we take the area of the section and divide it by the total force cutting through that particular region. We can see here we have a pre-compression of roughly 119, and then it bounces up here to about 140. So it's 120 to 140. The pink means that it's no good. It's not meeting some requirement. That requirement is actually defined under display. We have pre-compression minimum allowable is set to 125. So anything that falls below that would be flagged as pink. And we would have to then determine, well, what has to be done to resolve this low pre-compression in this portion of the slab. We can see it's a little bit low here also. And there are other areas where it's much higher. We mentioned earlier that we had these tendons kind of passing through here, like so. And so we had 2 here on one side, 2 on the other, and where those intersect kind of on these section cuts here, we get kind of double the force, and we get double the pre-compression because of how those converge down to that column. So those are little things you want to watch out for, and then we have, you know, fairly high pre-compression here again as well as there. So looking at the tendon layout, if I turn the tendon layout on, okay, one reason it's likely high in this zone, or excuse me, low in this zone, is because we have this set of cables, this cable, and then this cable actually falls outside of that design cut. So whenever we use this pre-compression number of tendons, it's more of a mechanical check, meaning the program just adds up the total number of cables times their effective force actually physically intersecting the section cut. So the other approach is to use a finite element based approach, where we use the axial force in the plane of the slab to calculate the force over the area. And you'll see when this is low in this pre-compression number of tendons check, it actually might work in FEM. So this is the FEM result, where this curve is actually based on the axial force, which could be subject to loss, restraint loss, due to position of tendons, position of supports, releases, the actual fixity or boundary conditions for the supports, and so on. So there's a couple of different ways to check this, and the user needs to determine the best possible way that is in correlation with how the slab will actually be constructed. If you have conditions or details that allow you to provide shortening of the slab, for example, release details, pore strips, etc., then you might just want to use a simplified check like number of tendons. but you also have to make sure that you have reasonable justifications or rationale behind why one area might be low and why one area might be high. For example, this is low because this tendon on the boundary, its entire effect is being felt by this strip here. So in reality, a portion of this force in this cable is going to leak into this strip. So we might be able to make that justification, and it happens on the top and the bottom. Or we might actually, instead of using a 4-foot spacing of distributed tendons, we might have been better off using a 2-foot spacing for better refinement of the forces in the slab for this particular check. But again, here we have a couple of locations where we have to make those types of decisions in this model. If we go to the other direction, we have, again, areas where we have low precompression, and here we just simply may need to increase the number of strands. So this is roughly 124, 125 into 115. In this case, I know that I don't have, because it's the banded direction, I don't have the same type of issue as in the other direction. So here I would probably just increase the tendons enough to where this area meets 125. I would do that for this strip, and also this strip. And then once you've made those changes, we then could reanalyze, redesign, and recheck the conditions. Other checks that would be necessary would be, let me go ahead and turn the tendons off. We would need to check, I'll go back to the X direction, we would need to check stresses. So we can see in the X direction, the bottom stresses are within the allowable limit for tension and compression. Tension is usually the biggest cause of issues in terms of being overstressed. And the allowable based on 5,000 psi concrete strength is 424 psi, and that's in tension. And you can see we have tension here. Positive is a tensile value. Maximum we have a tension of 240, which is far below 424. So the slab in this direction is acceptable from that bottom stress perspective. If I switch to top stress, we have one section cut that does not meet top stress, and that's this one. This allowable, again, is 424, and we're at 534. And if we look at the moment at this section, you can see there's a fairly high negative moment there relative to the column below, or the two columns here, and so on. So the program or the user has to be aware of that, and knowing that we have an overstress condition, the user then has to determine how that can be rectified through use of just manual modification of tendons or through use of the tendon optimizer. The tendon optimizer would allow you to optimize this particular span so that you can get an increase and determine the increase in force necessary to meet the stress objectives here. If you use our YouTube search option and search for tendon optimizer, we have specific videos of how that optimization process is done. If you wanted to use a manual approach, we would then have to adjust, let's say, the number of tendons or the profile. If we look at this cable is already maxed out. We cannot adjust the profile anymore. We could potentially increase the number of tendons for this tendon and this tendon, which both affect this stress, as does potentially these two cables, more so this one than this one. So if we wanted to modify these two cables, we then would say, well, is the precompression going to be affected in the sense that it's going to be too high? It's going to cause a precompression of over 300 if I add more post-tensioning to these two cables. In other words, increase the force. And I would come back and just look at the precompression. Our precompression here is about 150. Maximum is around 300. So we have some flexibility in increasing the force for those two cables to try and resolve that overstressed location. In the other direction, I'll switch this over to the Y direction. Let me go ahead and turn the tendons back off. You can see our top stresses here are acceptable. Again, the user could review these in more detail by reviewing each value. with a little more clarity, and the bottom stresses are also acceptable. So for this particular design, we have to add a few more cables to meet pre-compression, and we also have one issue where we have overstressed top fiber conditions at this location here. So there's just a few issues we have to overcome. Finally, we could check balance loading. If we check the balance loading percentages, we may be overbalanced in a few spans, and clearly we are. For example, here 171, 154, we have tendons in those spans. If I turn the tendons on again, where we've maxed out those drapes, and I can turn on the CGS here to see that those are maxed out. So the question then becomes, well, if we want to reduce the load balancing percentages, we're going to have to raise, if we keep our force the same necessary to meet pre-compression, we're going to have to raise the tendons to eliminate some of the uplift. The question then becomes, can we do that? Well, what the user may need to go back and check is, what's our stress? If I raise this tendon, this stress is going to grow. So we have, again, flexibility. The maximum is 424. That's the design constraint we've put on this slab, 6 square root of F prime C. We have room to actually lift those tendons to reduce the balancing. So that again is something that the user could do either manually or through use of the optimizer, the tendon optimizer here, where we would look at kind of span by span or tendon group by tendon group, and how that could be used to determine what force and profile may be needed to meet the design objectives. The last thing we're going to do is just show how we can generate reinforcement for this slab. So we'll assume that the tendons are what they need to be in order to meet all of those design requirements. And ultimately, we want to design the slab for reinforcement in addition to the post-tensioning. So if we go back to floor design and we calculate the rebar plan for the entire envelope, this will allow us to then generate reinforcement layout for the slab with the current conditions of the post-tensioning. Again, we're assuming that the post-tensioning is the right profile, the right force or number of cables, and the right placement for the design of both service requirements and strength requirements. And this ultimately becomes the layout of reinforcement, non-pre-stressed reinforcement, in addition to the post-tensioning. If you wanted to determine just reinforcement maybe for strength, I can do envelope of strength. So we have a lot of PT in this slab. We actually only have a few locations where we need reinforcement to supplement the post-tensioning to meet the demand. For example, here we need 2 number 8 bars in addition to the post-tensioning. And if we go and turn our strips back on, I'll go down here to investigation, moment capacity with demand. And you can see that the blue is the negative capacity from the post-tensioning and the calculated rebar, and the green is the positive capacity. And you can see where this gray demand curve kind of meets the capacity curve, that dictates the amount of rebar for strength in this case. That demand capacity ratio is 0.99. That's shown there and there. And if you double click on this, we can see that strength is controlling the amount of bottom reinforcement needed in addition to the post-tensioning for this section. So there's a few investigative options here graphically that we can review for the reinforcement design. If you have any questions about this video or need assistance and training, please contact us at support@adaptsoft.com. Thank you.